So let's introduce today's speaker. Anupam is an assistant professor at Plaksha. He did his postdoc at Microsoft Research India in the Societal Impact Group, Societal Impact through Cloud AI group and he did his PhD at IIT Delhi Technology Group. He's currently working in geospatial and embedded perception for agri-urban sensing, using satellite images and ground sensors to understand the interconnectedness of the world. He is excited about applied research in domain of agriculture and urban planning. And when I read out excited, I actually mean excited and it's not just a cliche. So over to you, Anupam. We love to hear from you.
Thank you so much for inviting me here, Nipun. Nice to see so many of you taking out an evening of yours to listen to me. Great. So I guess we'll dive right in. I'm running this group here called Geospatial and Embedded Perception, and I started this when I joined Plaksha. And the context is that I was trying to find something which can sort of give me more insights into what's happening around me, because I generally sort of imagined myself as a uh, societally isolated person. I did not really understand ki kya chal raha hai. So that's sort of was the inception of this group. And satellite images was something nice. So typically images speak 1,000 words, but I believe satellite images could speak a million words. And the reason is because, when you look at a particular location, you're not just looking at something which is, just in the image. It also says something about the people who live there, how they have evolved over time. So different types of satellites provide you different resolutions, and they also provide you insights at from for different kinds of things. So this is examples from the agricultural domain as well as the urban domain. So you can see we have high resolution imagery, which can even extract what exactly is the building area for this particular building. You also have low resolution imagery, which also has different types of bands. So it can even see underground. It can even see uh, thermal. So it has all of these superpowers, which, because humans are limited to one geolocation, they're not able to form a broader context about what is happening. But when you look at satellite images, you can look at the entire time series, you can look at all of these different modalities, and it gives you insights that are sort of not easy to imagine as people on Earth. So, my work is in two areas of impact. One of the areas is urban heat islands, and the other one is agriculture. So, I'll speak about urban heat islands first. Uh, Urban heat island is essentially a phenomena that when you start building a lot of roads, buildings, etc., in a concentrated region, which we call cities, we basically also introduce a lot of heat within the atmosphere of this particular city. So whatever heat is coming in is getting trapped. There are dark surfaces. Most roofs are also dark. So these will also trap heat. Sometimes buildings are built very close together. So this also traps heat because the air cannot circulate between these areas. So what ends up happening is that you have this urban heat island around the city region, where the temperature within the heat island is much higher than any other surrounding areas, which might be rural. So, because of a large amount of tree cover, lakes, water bodies, etc., within the rural regions, you would see much lower temperatures there as compared to the urban area. So, are there ways of designing cities so that the urban heat island does not, happen? I guess so. There are a lot of architectural urban planner perspective to how do you build cities which can affect urban heat to a limited extent. And you will see different types of things here. If you could use solar and wind power, it's possible that you will be able to absorb that and not use thermal power plants, for example, to put pollution, which will also heat up things. You should have indoor ventilation so that you don't need more electricity. You should have air corridors and green spaces, which will also help you sort of circulate the heat throughout the city, right? So, and even designing better transport systems, for example, If people are not driving vehicles, they're using public transport, it limits the amount of pollution that you have in the city and therefore also cools down the city by a significant amount. So these are many different interventions that people try out for urban heat islands. And we looked at this one particular intervention, light surfaces and high albedo surfaces. So this intervention is basically saying that on top of a building where you typically have a black or dark surface, try to put something which is more reflective so that before the heat starts radiating within the atmosphere, you can reflect it back into the atmosphere. So the cool roof, as they call it, is special because this as an intervention does not require any change in user behavior. You put the roof, you can still keep living the same way. It is profitable because it reduces your energy consumption, which also lowers your electricity bill. So with a low capital expenditure, you will be able to make profit on whatever cool roofs have been deployed. And it's also easy to, push people to do it because a single decision maker is typically involved, the one who owns the building, right? You don't have to really go to the municipal corporation to get a permission or something. So this is an intervention is quite interesting, and therefore governments have also been sort of pro about it. So governments have also been rolling out policies on how do we increase the adoption of cool roofs. For example, Telangana now has a policy where all of the cool roofs, all of the new buildings within new commercial buildings that come up within Telangana need to have a cool roof. And they also have a 2030 goal that they want, I believe, 300 square kilometers of area under cool roofs. Right. So Hyderabad is the perfect sort of climate also for this intervention because it doesn't get too cold, but it gets hot within the summer. So cool roof works across all the 12 months. Right. So one of the things that we were looking at is how do we support the policymakers in order to, make better decisions about where to invest money in putting more cool roofs. And how do we track from a regulatory point of view? How do we track whether new buildings that are coming up will also are putting cool roofs or not? Right. So we developed a cool roof detection method. In this method, we basically use the footprint extraction method using Maxar imagery. This is some work by Google where they're doing continental scale building detection. Then we developed a method for reflectivity estimation using RGB and NIR, high resolution, high frequency imagery. So this is from a company called PlanetScope. PlanetScope has a low Earth orbit constellation of satellites where you can get everyday imagery for the entire Earth using their satellites. Right. So because it is a constellation, you have a lot of pass through over the same areas, which allows them to capture this. And they also do it at a very high resolution. So they have a 3 meters resolution uh, on this image capture. If you compare this with an 8-band albedo measurement, which typically is done, albedo is basically the reflectivity of the surface. So if you compare this with 8-band albedo measurements that are typically done, these are very coarse because each pixel is very small. So it's not usually possible to isolate these smaller buildings and say whether they have put cool roofs or not. So that is the challenge here. How do we sort of use this? But okay, so the 8-band measurement that is here is actually able to measure in SWIR, right? So it is able to measure in shortwave IR what exactly is the albedo of the surface. So if you're capturing SWIR, then you're actually capturing whether heat is going out of the system or not. In the case of NIR, this might just be reflectance off of it, might not actually be taking heat out of the atmosphere. So, uh, so the building extraction part, which Google did, is based on pre-training task. Are you guys familiar with pre-training deep learning concepts?
I think most of the classes
Okay,
have studied those.
right. So within
So
deep learning,
another request, Anupam.
yes,
So given that it's very hard for the audience to directly ask, so perhaps every few minutes at some strategic points, you could just pause and see if there are some questions. That would just make it easier.
sure,
Otherwise, I will have to just look through them and see if they have a question.
sure. Yeah. Okay, so within deep learning, basically there is a paradigm called self-supervised learning where you run a pretext task which allows you to learn recent embeddings about the images. So in this case, the pretext task that was used was basically predicting which area of the world is an image coming from. So now you're looking at roof images and you're trying to predict which area this is from. To be able to do this task well, the network has to learn properties of the roofs, properties of the images coming from certain locations. Right? So it also learns the properties of different areas within the world. And using these properties, it forms a decent base of embeddings, which it can use in downstream tasks for building estimation, building polygon estimation. So we use this as is from the dataset that has been released by Google, and then we on top of it basically build a reflectance estimation. So this is the difference that you would see in a
Anupam, I
cool.
have one quick question. If you can just go back to the previous slide. The pretext task, pretext you meant. So did you mean when you which area of the world the image is from? Is it typically taken as a classification task or some latitude, longitude they're trying to estimate from the images?
So not that long. So these squares that you see here,
Okay,
basically they're
I see.
trying to say which square this is from.
Okay,
Right. So these squares are also fairly big. So you would see probably Bangalore and Hyderabad is in the same thing. And you know, so
I see.
it's not a very difficult task that you have to point out the lat long, but it is still trying to learn what kind of uh, buildings exist in this region.
Okay, thank you.
So this is what cool and non-cool roofs look like in a composite band. So this particular image is a mixture of RGB and NIR, and you would see that the cool roofs are actually shining quite brightly, which makes it easier to sort of detect. Although, so the task is not very straightforward that you can threshold it, because on different days you will have different reflectance levels depending on which angle you're capturing from, what time of the day does the satellite pass through, and so on. Right. So we need to build some features which can give roof level sort of feature description of how do you classify the reflectance. So the second problem that we face here is that shortwave bands are only present at a very coarse resolution. So to give you an example, the big black square that you see, this is 1 pixel of the Sentinel satellite. This is at 10 meters resolution. So you can see that for this very small building, using this pixel to classify whether this is cool or not cool is, not cool. So therefore, we try to extract what are the points where you can do this at 3 meters resolution. So when you extract the planet scope pixels, which is these 3 meter pixels, we build this classification pipeline, basically using the building footprints and the planet scope imagery. We define a certain set of features and we classify. So that's one pipeline. But the second more interesting thing is that when you try to estimate the absolute reflectance of that place, so that you can do by extracting these buildings, but we had to create a training set for a derived albedo. So because we do not have SWIR bands in PlanetScope, we basically used a regression from RGB and IR bands to the albedo, so in the hope that it learns some semantic properties where it can also, uh, you know, give you actual albedo of the surface. So we created this data set for images which have a lot of overlap with respect to the underlying buildings. So wherever you have a lot of overlap between the big pixel of Sentinel and the smaller pixels of Planet, we took those points and basically did a regression model for predicting the albedo. So another aspect of this is, so once you're detecting which roofs are cool and not cool, a city like Hyderabad could, for example, see this distribution on how is the adoption going on in different regions. It's also possible that some regions of this place are at a socio-economic disadvantage, right? They may not have money to put cool roofs. So in that case, they can also come out with facilitation plans or subsidies for those regions itself. The second area where this kind of a model is useful is rather not just this kind of a model, even building footprint extraction is enough. So we were working with the Uttar Pradesh government where they wanted to plan out which district should they allot which how much funds. So here again, building roof footprint extraction gives you a very good estimate of what is the relative uh, amount of roofs that are present in each of the districts, and therefore where do you need to spend more. So yeah, we built a dashboard out, and here you can see different colors for, although probably bad choice of colors. This is a darker color, this is a non-cool roof, and this is a cool roof. And here you can see all of the cool roofs which are present for Hyderabad. So here you can go building by building and do an exploration of what exactly is a cool roof and what is not a cool roof. Uh, so maybe I can stop here for questions.
Are there any questions in the audience?
So how is the cool roof is being identified? What are the features that has been considered?
Okay, so I haven't put the exact list of features here, but it is basically things like different percentiles of the reflectance level, LBP patterns on the roof, right? So these kind of things. You basically different number of pixels are returned for different buildings. So you can't use a fixed length method. You can use only the features that you define on this, and then sort of collapse them, reduce them to the same number of features. So I believe we use 64 features, just things like median values, 25 percentile, 95 percentile, and things like that.
Okay, other questions? I had one other slightly broader level question. What is the typical payoff once you shift to the cool roof and assuming some units? And then what is the buyback? Like why should people be from a money perspective also?
Hmm.
Does it make sense? And for how much time do they need to wait till
Right.
they get the buyback?
So cool roofs are available in different types of materials. They can be, as cheap as a paint that you put on your roof versus cool roof tiles. So I believe the paints are just about 1.2x the cost of the regular thing that you would do. And they the downside is that they will also last to a lesser amount of time. If you put tiles, they last for about 7 years before they stop reflecting, and the payoff you get is in about 3 years you will be able to recover the cost of putting the cool roofs by the reduction in your electricity bill.
Okay. Okay, thank you. I think there are no. There's one other question.
And I had
Yes.
more doubt like here Hyderabad I believe is a city where it doesn't receive much rainfall, right? Like so I come from a part where it rains for 4 months for a large amount of like precipitation happens. So there is there any study conducted over such areas or just based on the hot or cool climate like that it has happened, the study?
Good question. So there are different types of studies here. Some people have also put cool roofs in snowy regions. Some people have put it in rainy regions. So essentially, the choice of material that you put on the roof will be different. You would not want to put a paint rather than putting a tile. So you should probably prefer tiles, because if it's going to rain a lot, then your roof paint is going to wear out too soon for you to actually receive benefits. But as long as the temperature is moderate, cool roofs are a great thing to put in. If the temperatures are extreme, then it helps the structural integrity of the house, as has been discussed in some snowy regions. But I'm still not sure. I don't think that study has been done on what is the effect if you put it in, for example, North India. So that aspect is still not clear, because I believe, for example, Delhi's peak electricity consumption is not in the summers but rather in the winters, because just cooling systems are more efficient than heating systems currently, right? Any?
There's
Yes.
another question. Yes. You have to be a little louder.
Sir, both are prediction. So how ground truth is not available in there. So how do you assure that the prediction are correct?
I
Could you
could
get the
not hear
question?
the question.
Yeah.
No.
So the question was that how are you getting the ground truth for cool roofs?
Good question. So basically, some companies have policies that they will only put cool roofs. So Infosys happens to be one such building. So they themselves have significant number of buildings where they put cool roofs. Apart from that, we were working with NRDC, who also provided us some data on where there have been sort of programs of the government to put in cool roofs. So there we have to manually identify the cool roofs and annotate them.
I see. And is that manual annotation done using the high-res satellite imagery? Or
No,
you do
we
have
use
field
PlanetScope
imagery?
imagery.
Okay,
Planet.
planet.
PlanetScope and the high-res is Maxar. So just distinction between the two. Even Sentinel is called high-res in some contexts, by the way. So
Okay,
okay, so shall I move on?
sure.
Okay. So the second application that I'm going to be discussing today is walkable cities towards reducing UHI. Essentially, to move is to live. Walking is the medicine to both body and as well as mind. And it is also a human equalizer, irrespective of how rich you are. Walking is good for you and walking is accessible to you in most cases. Right. So it makes sense to put a lot of emphasis within the cities to make sure that people can walk freely. Some of that emphasis might also look like this. So this is a rendition, artist's rendition of how a walkable street looks like. So you will notice that there is, a large pathway for pedestrians. There is a large pathway for cycles, large pathway for, people to sit. And there are also play zones built out here. You will also see mixed land use. There is a commercial property here, but there is residence here. So people don't have to really go far out if you want to go to a restaurant. They can just go to a nearby place by walking. Right. So these are some of the elements that you can see where the design of the street itself facilitates and encourages walking. So by putting play areas, by putting seating areas, you also make the place very safe for a person to walk by. If there is no activity in the street, it's most likely going to be a deserted street, which again people will be hesitant to walk on. Right. So given this context, how do we really evaluate whether our cities are currently walkable or not? So AI can help with walkability by finding a scalable and up-to-date solution to assess walkability. So what do I mean by scalable? So if you look at the current method of assessment of walkability, an agency, for example, so you might be hiring an agency where there are some people who know how to look at the walkable elements, etc. They will charge you about, let's say, 10,000 rupees for 2 kilometers, so 5,000 rupees per kilometer as a daily fee, and they will be able to do the assessment for an entire city in, let's say, 6 months, right? So that's not really a scalable mechanism because the amount of money that you will have to spend and the amount of time that it will take will give very stale information to decision makers who are trying to decide where to put more walkable infrastructure. So we want to be able to do real-time assessment of walkability, real-time as in, at least it can be refreshed every year, every 6 months. Uh, and the urban infrastructure assessment, we want to get to a level where we can do allocation of money as per the criticality of infrastructure. So where are most pedestrians expected should be the answer to where should you build next, right? And assessment of the use of infrastructure. So if the infrastructure has already been built, are people actually using it or not? So the second question is a bit tricky to answer. We will first look at the first one. So this is the metric that we came up with in a workshop with some urban planners and Nagaro. So these are sort of the index versions that we are building out. So the index version 0 is just looking at the crossing density. So how much opportunity do you give your pedestrians to cross the streets? Index number 1 is looking at footpath coverage as well as tree cover. It's also looking at whether they are lighted or not, whether the land use is correct or not, right? And walkable space, active frontage. Do you have enough space to walk? Active frontage means, are there shops on the road which will help you be safe as well as, have a human element to it? As well as is there encroachment on the walkable paths? And finally, is it clean? Is it scenic? Do you have seating space for people who would want to sit? Right. So these are sort of the index versions that we want to build out for detailed assessment of walkability. What can you do if you have, these kind of elements detected? So essentially, if you look at this intersection, this is an intersection near Plaksha, where let's say I'm going from this point to this point. right? So Google Maps will currently show you, okay, basically go in the middle of the street, then figure out some way to cross the street, right? But you might also be able to do detailed walking directions. For example, there is a zebra crossing here. So you might say that, okay, there is a good tree cover within this, walk on this footpath, then take the zebra crossing, then maybe, choose this side instead of this side because you'll get tree cover here and you won't get tree cover here. So that kind of a granular directions can also be done if you know exactly what elements are present where. So since you guys are familiar with deep learning methods, so this is a unit architecture which just does zebra crossing detection. So with geospatial images, you can project them back onto the satellite and they look very small, but the images that we actually used were, this big. So we were using chips from geospatial imagery to capture the zebra crossings in the image, which is a reasonably easy task. So again, we were using, so we found that we were also able to sort of recognize where the zebra crossings were built out fully and where they were only half of the zebra crossing was built out. So this is also, potential information to the municipal corporation where they want to maybe fix that situation where there does exist a zebra crossing, but nobody can cross using the zebra crossing. And we got decent precision and recall here. So the sets that you see is the two cities that we looked at. Gurgaon 123 is basically 3/4 of Gurgaon, and Mohali 123 is M123. And we use this as the training set. This is the train set, and we found good precision. And even across cities, we found decent translation, except Mohali because Mohali had lesser number of zebra crossings. There are other elements that you want to detect, for example, foot over bridges. You also want to be able to quantify the tree cover that is available on these paths, right? Because if there is tree cover present, one, temperature will be lower, and second, you will have shade to walk on, right? So you will also be protected against rain, etc. At least, light rain. So these are all the elements that add value to the user directly, but also give this information to, let's say, a municipal corporation who might want to just put more trees in some regions. So using satellite images, you can do these elements, but what about the rest of them, right? So for rest of them, we use the street view imagery. So you have the Google Street View images here, and you run a segmentation algorithm on top of them, where you segment out the road as well as the footpath, trees, and so on, and then you project them back to the satellite images. So this kind of an approach helps you detect not just footpaths, but also encroachments on footpaths and so on. So now there is significant coverage of cities with respect to Google Street View as well as Map My India. So both, if you can use that imagery, then you can also do this. So I believe the terms of use of this imagery do not allow you to train on this image. So we were only doing inference on this image using the API. Okay. So the next question is, you have built out a method where you can detect these elements. But is it important to evaluate in the entire city? Or should you rather choose paths where people are more likely to walk, right? So here we use the data that is present on OpenStreetMap as well as from municipal corporation website. So for example, within Gurgaon, we looked at where are the residential zones and where are different types of commercial activity. For example, public transport terminals, so bus stops, commercial, industrial, retail, bank, ATM, etc. So these are sort of common uses for which people might be willing to walk, right? So these are, for example, the number of paths that we found for Gurgaon, and you will see that the trails that you see here is basically people sampled from the residential areas going towards some of these outlets, right? So again, if you have a path which is heavily used because there are a lot of, let's say, commercial things this side and a lot of residential people this side, then it makes sense to prioritize this path over other paths, right? So this is how you isolate paths which might be important for a city, and then for each path that you see, you run an assessment using street view and satellite view images, where you can detect which elements are already present and which elements can you build in order to make life easier for X number of people. So we also weigh this by the population density of those regions, which is released in a census. So there are forecasted versions of the census that you use for estimating the current population, although they're not that accurate. So hopefully, if we have a 2025 census, this will be all up to date, right? So I don't know if you guys know, but basically we had a 1991 census, then we had a 2001 census, 2011, but there was no census in 21 because we were in COVID, and it hasn't happened ever since. So we are right now in a situation where we don't really have a latest census number to look at. Right. So all of this information is basically now projected to satellites to make fine-grained decisions for different types of elements. Uh, yeah, I won't go into detail here, but maybe I can talk about it later. So this is essentially the process that we are suggesting, that you find the walking demand using the land use. So sampling people from the residential areas going to commercial areas or some utilities. Then you do the path assessment using both satellite images as well as street view images. And finally, you provide insights on where to build infrastructure and what is the utility of the built infrastructure, right? So what might also happen because of socio-economic forces is that there is a rich society which will get all of the pedestrian infrastructure, even though not many people are living there. There is a large amount of car ownership, but there might be a place which does not have so much car ownership, and there it is not a matter of convenience. So it also becomes a matter of whether they will have occupation or not. For example, a woman who lives 2 kilometers from uh, or 3 kilometers from a bus stop might just not walk because it's not worth the effort for going to work. And if they take a e-rickshaw or an auto, then it just becomes a uh, financially stringent task for that to happen. So here, eventually, we want to do a multimodal capture where we are using satellites, land use, street view, but also let's say we have an app. So we want to be able to use IMU as well as mobile carrier localization to find out where exactly are people walking. So this is where the second part of what I said comes in. So this is trying to assess where should you build infrastructure, and this is where is the utility, what is the utility of the infrastructure that has been built out. So using this data, then basically all of these services will be built out. These are services that use this data and might have outputs for different kinds of metrics. You can use these different kind of metrics to sort of estimate how is the walkability in this region. These are some sample images of detections that you can get from street view images. And there is also similar activities being done in China and other cities where people have looked at street view segmentation and built out different types of metrics which are useful for the city. Okay, so I'll stop here for more questions.
Yes, questions?
So elements, zebra crossing and other elements, did you train yourself or did you use pre-trained models?
Could you just repeat the
Yes.
question? Did you use pre-trained models or did you train on some of your own data for elements like zebra crossings?
So zebra crossings, we did not find good data sets, so we had to build it ourselves. For tree cover, we did find forest cover mapping data sets that were sort of translatable to the cities as well.
Other questions?
So have there been any study done for the higher the walkability there is, the higher the noise there will be in the environment?
Well, I'm not aware of such a study, but I think it has also been shown that higher the walkability, higher is the economic value to the local businesses. So I guess it sort of cancels out the noise.
I mean, there in marketplaces there will be a multiple people walking and there will be a huge noise. That's why.
Right. Yeah.
So
I
I
guess
think
more
there's
lively streets.
Yeah, I think perhaps there's another element or understanding of walkability. So I know that in certain parts of Delhi, the IAS officers just cleared out certain parts. I don't know how many of you've heard or followed those. And earlier you had a lot of vehicles. Now all of the vehicle entry has been stopped. So it's now you only allow pedestrians, and all the other vehicles as well as rickshaws, etc. They have to stop 1 kilometer something apart, and it looks like a much better transformed, beautiful city. So I think that's the other. So I had another question regarding walkability, and because you've stayed in Bangalore, right, close to the Microsoft office, you know that there are certain parts which we have figured out that it's extremely difficult to just cross the road, etc. So then we just stop taking those. Otherwise, like they're the good roads, etc. There is a decent amount of tree cover also. So how would you
Yeah.
factor those kind of considerations?
Yeah. So for example, crossability is already factored in as an index where
Okay.
so we we are looking at, for example, these pathways in terms of the street network, right? But now if those within the part of the street network there is some aspect which is really difficult to do, then that is a higher priority for the municipal corporation to actually build up.
Okay, so I'll actually rephrase my question. I was thinking more in terms of, let's say the infrastructure is good, it is just that the driver behavior is not ideal, and that makes the walkability index low. Because of that, people find it harder.
Yeah. That's too tricky to
Yeah.
sort of do here, but yeah, uh, I have seen sort of interesting zebra crossing implementations where it feels like you're actually going to fall and things like that. So that might be one way to improve driver behavior, but that's obviously a much harder problem.
Other questions?
So one question, like which satellite imagery was used for this zebra crossing detection?
Zebra crossing, we were using the Maxar imagery, which is through Google.
Okay, so then like it will have problems in publishing these things, right? Because you are training on them.
Correct. So we are yet to figure that problem out.
Okay, thank you.
So, and I have another slightly broader level question. So again, it seems that the municipal corporations do have a lot of the data. For example, now like every tree that they have to chop down, they will have to maintain a record, etc. So it's clear that they have an active record. I don't know whether it's geotagged or not, whether they have the latitude, longitude corresponding to each tree or not, but it seems that the municipal corporations have the data. It's just that it is very inaccessible. And I believe your work is in from the other end saying that we will just use AI and satellite imagery and we do not need to manually do those. But there still seems to be this huge plethora of data sets which are available in a very unorganized, or rather they contained in a very unorganized setup. So do you plan to somehow use them either for adding to your data or for grounding your data for ground truthing, etc.?
Yeah, very good point. So on the example of trees, by the way, so we had a tree inventorization project as well, where we were segmenting trees and then putting them on 3D. And we were working with the Department of Environment in Chandigarh, who also said the same thing, that we already have a portal where people can actually go and raise requests on, we want to chop down this tree, or this tree is becoming a hazard, or things like that. So I believe the opportunity lies at the mix of these two places, where currently that interface is so closed that people A don't know about it, plus B it's not easy to use. So if you build out the implementation of this thing in a way that people can now actually go and raise complaints on it, basically enter the operational pipeline of the municipal corporation through a better, uh, through a better visualization or through a better UX.
Okay.
So I believe that's the sweet spot.
Okay.
Okay. So essentially, how do we go from knowledge to value creation is sort of the question that Nipun also was asking. And from knowledge to actually delivering value to the local municipal corporation. So anybody who's worked with the government would understand that basically the IAS officer is the person who might get rotated quite often. The minister also gets rotated quite often. So their sort of the value proposition is hard to deliver. But I believe if you make things such that the person who's actually had to do work on the ground, their job is easier, then that lot of value creation can be sort of maintained for a longer time. But yeah, so lot of tricks and bits there. So there's no right answer for this right now. Okay, so how much time do I have, Nipun?
Just a second. So it's 5:44. We can go till 6:20, but we can end earlier also. We
Okay.
can max go till 6:20.
Great. So I will also cover the work that we do on agriculture. So this is
Sure.
the geospatial computer vision for agriculture. I do this with Professor Shashank Tamaskar at Plaksha itself. The picture that you see here is of a smart farm in Plaksha. So we are actually growing cane within the campus. We wanted to have sweet sugar cane juice, but we also put a lot of the IoT sensors here for monitoring, and we also control the soil for some of the biochar experiments that we do. So Plaksha is basically organized as centers. We also have people from biology, people from robotics, etc., all working together on the agricultural problem. So we use this as a common test bed for different types of experiments. So there are two types of work in agriculture largely. So there is a top-down work where we want to do India scale work to benefit the agricultural tech ecosystem at large. These are things like you want to just detect anomalies on the images, right? Or what kind of SSL models can you build for agricultural imagery specifically? And there is a bottom-up kind of work which is required to actually instill belief in your systems, because these are field scale experiments where you're actually collecting agronomic data, getting them tested in a lab, and then presenting the facts, right? So these are field scale experiments, for example, water and nitrogen stress. If you've noticed, the top down tree is actually a tree which is bottom up, right? But that's because we are in CS, so our roots are at the top. Okay, I guess people either didn't get the joke. So here are the beneficiaries of such a system. So if you build out an agricultural informatics system, essentially three people get benefited. The farmer can receive personalized information. So currently, if you are a sugarcane farmer, you're growing a variety XYZ in a certain climate condition, the department will come out with a sugarcane report. So now you have to read through all of that and then think whether this applies to my region or not, right? And then finally use that information to do something on the ground. If you can provide geospatially relevant information to this particular farmer, they immediately can stop that information access overload and do more things with their farm. Bankers and insurance also get a real-time visibility into the farm. So not only can they see what you're growing right now, but they can also see what your past productivity has been, right? So this is a major sort of a problem for especially in rural areas where you don't have formal credit scores because you don't have a lot of income tax payments or things like that, right? So the actual productivity in the farm in this case acts like a proxy of your credit score. And finally, government also gets access to where exactly are the crops going to grow, how much are they going to grow, and therefore how should they set policies for pricing and markets such that it's beneficial for everybody. So for these three beneficiaries, we will look at a certain set of applications which are applicable. Right. So let's first talk about anomalies for farmers. So this is an approach where we're trying to do label-free anomaly detection in aerial agricultural images. So this particular work is in drone, but we want to eventually will do it on satellites as well. So this is what anomaly detection looks like in UAV images. So you have a certain input image, which is captured through a drone. In a typical SSL model, you will, pass it through a master autoencoder kind of a thing and try to reconstruct the original image, right? And if it is trained well, then it will reconstruct the original image. But if there is an anomaly like this within the image, then essentially what you reconstruct is a normal field. So the difference in these two, which is the original image and the reconstructed image, actually gives you what are the anomalies in this particular region, right? So this is the sort of high level funda, and we are trying to optimize this process in a certain ways. So one, we used SwinMAE for the reconstruction rather than just using MAEs, because in agriculture there are both fine scale as well as large scale. Are are most people aware of SwinMAE?
I don't think people are
Okay.
that much.
So SwinMAE is basically the brother of a transformer. I think I have an architecture diagram later on, so we'll come back to it. And second thing that we were doing was we want to use no labels absolutely for any part of the pipeline, and I'll show you how. So these are the kind of anomalies that are present typically in agricultural imagery. You have a wheat cluster coming up somewhere, you have a waterway which has suddenly formed between some part of your land. If you're using a bigger tractor, then you might have a case where you have double planted in some regions, so the yield in this area actually, the plants compete against each other, so the yield actually goes down. Similarly, you could have different types of deficiencies or uh, artifacts of actually the machines that are being used. So the benefit of doing this problem as an anomaly detection problem rather than a supervised problem is that it varies a lot in shapes and sizes, right? And it can have multiple causes irrespective of what is happening. So we want to build a general algorithm which is doable for multiple crops, causes, as well as modalities. So in the typical anomaly detection literature, you would find anomalies such as this. Right? So if you're building, for example, an anomaly detection pipeline for this capsule, and you will see this crack here. The only difference is that within these type of problems, the the notion of what is normal usually exists within one image. Right? So you can look at this capsule and say whether it is normal or not. But to be able to see that for this field, you will have to look at the rest of the field and also say, okay, whether this is normal or not. So that notion of normality is slightly different for agriculture, which is why the same techniques may not work as is. Uh, so SwinMAE is basically uh, a slightly different architecture as compared to a normal transformer, where you basically break down the patches further and further, so that you can capture both small level detail as well as high level detail. So this kind of aggregation of detail from all levels allows you to look at very small anomalies as well as very large anomalies. So this is known as local and global features. Okay. So coming back to this, so using the input image and a window masking approach, now you're trying to construct the anomaly. We were using a window masking approach because we wanted to hide the entire anomaly, and if it leaks out through some of this random masking, then it will basically also be constructed, and you won't be able to find out where the anomaly is. So the original work that was being done in this area was that you were separating out, if you look at this upper pipeline here, you were separating out the anomaly class. For example, where is the weed, where is double planting, and you were training a master autoencoder of the rest of the data, which is treated as the normal data. But you can imagine that whatever was treated as being normal also had anomalies of certain types. Right? So suppose you wanted to detect weeds as anomalies, you would keep weed separate, but take everything else in the data set as normal. So waterway was normal, for example. So this was not ideal. So we wanted to do a method where we could remove this particular step where you have to separate out any of the images and still be able to train your model. So we basically just go from this, that you collect the drone images, train your master autoencoder with an anomaly suppression loss, which I will come to. And finally, you use this trained MAE to detect the anomalies. So this is what the anomaly suppression loss is. Essentially, while training, whatever is the wherever you have high errors with respect to your reconstruction, those errors are now multiplied by this weight, which is max of E minus Cij, right? So wherever you have, for example, anomalous samples, you will have a high error, and I'm putting a weight which is very close to zero on those regions. So what this does is it lets the model train on whatever is a normal sample, leaving out the extreme cases, right? So wherever the errors were very high, I made them close to zero so that I can sort of train the model on very low error, on the normal samples rather than treating them on the anomalous samples. So what this allows you to do is you don't have to explicitly say what are the anomalous and what are the non-anomalous samples. But can anybody figure out a problem with this?
Anyone from the audience?
Okay. I couldn't hear him.
Yes, so the student is answering that maybe there is a roof which is white in color in a field and it might get high error for that.
I mean, but that should be seen as an anomaly if you put a building in the middle of the field. But the problem here is more severe, which is that when you're trying to train a network with random initialization, you will have high errors even on normal pixels, right? So in this case, your network might not be able to learn something, which is nice. So we had a simple solution to this, which is that you learn decent representations by running for, let's say, 20 epochs, and then you apply the anomaly suppression loss so that it only suppresses things which are not normal. The idea is that you have some decent understanding of what might be normal and what's not normal. And of course, our method was able to beat the relative methods. Uh, these are some good examples of being able to detect anomalies. So you can see these light samples were also being detected. Uh, this is a water body that just grew here. Notice that it only isolated this region as an anomaly because this was large enough to seep through the masking process where it reconstructed some of this. Right. Similarly, double planting it was able to find, dry downs it was able to find, and so on. And these are some negative examples where so even if you have a tree shadow within the field, that does seem like an anomaly to this process, right? And similarly, if you have large areas, because you're doing it at a certain scale, if you have large areas within the image which is covered, then that anomaly also seeps through. So this is the kind of examples that you can get with this method. The beauty of the method, of course, is that you can do this, across different types of crops, across different types of imagery, and so on, as long as you can establish a notion of normality within the data. So maybe I can stop here for more questions. If you have any questions?
Any questions?
So I had the question in recent representation, like how you could do it, like what is the process, like run for 20 epochs, like how you get
Yeah,
that,
so
um, essentially.
the 20, that is empirically derived. I mean, we just looked at that when we stop at 20, we were getting the best results. So that is mostly an empirical observation, but there can be a better method where you just look at the gradients within this, within the network, but we did not implement that right now.
Still, sir, like I didn't get like how you learn the decent representative. You tried out 20 times masking random pixels, or what is the procedure?
Yeah. So the self-supervised loop that you were learning, which is that you, on a normal image, you were trying to reconstruct that image back by masking out, let's say, 70% of the image. So you keep doing that without any anomaly suppression loss. So you were doing it for all the pixels. So since majority of the pixels are going to be normal, your network is able to learn what is normal for this particular data set. And then you introduce the anomaly suppression loss to also let the anomalies go through.
Okay, any other question? No, there are no other questions.
Okay. Great. So maybe the last method that we are also currently developing is the agricultural self-supervised learning. So if you look at SSL for agriculture, the only thing that's unique about agricultural images is that it follows the nature's calendar, which is if you sow, it'll grow, and if you grow, it'll eventually be harvested for something. Right. So how can we capture this particular process in a self-supervised pre-text task? Because currently, if you look at the kind of methods that SSL is done on, these could be things like jigsaws, where you just, uh, make a puzzle out of the input image, try to predict the image again. This kind of a thing is good for spatial understanding, but it is not actually capturing this thing where you could be, in an entire cycle. So, so how do we capture this so that our methods can learn this cycle inherently? So one insight here is that because time is key here, uh, the temporal frequencies, how quickly your pixel is changing, might also be able to reflect whether this is a crop or not, right? So the first thing that we tried out is basically the temporal frequencies of these regions on both the urban area as well as the cropland. See, in the urban area, you will see that the frequencies are more or less similar across the entire patch. I don't know if the projector is good enough to see this, right? But you will see that these are mostly the similar color. But if you see it in the agricultural context, then you will notice different colors in different regions, right? So with these different colors, what you can signify is that you have different frequency of data in these different locations, which is actually the different types of crops that is growing. So looking at this image, it is hard to actually say what exactly is happening in terms of the crop. But looking at this frequency map, it turns out to be much easier. Right? So this is insight number one. And the second thing that we tried to do, we tried a couple of architectures. Maybe I'll just talk about this one, which worked best. So here XT1 and XT2 are the two samples, which is satellite image at T1 and satellite image at T2. And T1 and T2 are the timestamps. So just the date of the two satellite images. So we used XT1 to derive the latent representation ZT1. And then we created this temporal predictor, which used the T1 and T2 timestamps to predict what the next frame is going to be via a decoder. Right. So in this case, if you're trying to predict the next temporal frame, can you guess what kind of things would this network learn? So I'm giving you only this particular image, and I'm asking you to predict what is going to be the case in 3 months.
Does anyone in the audience want to try this? Does it help you to learn how the different cycles of cropping,
Correct.
the seasonality aspect, which you were mentioning, is the key insight?
Hmm. So to be able to correctly make this image, you first need to understand what is the crop that you're growing here and what is its cycle, right? And only if it is a crop and there is a cycle, can you say that, okay, this will be harvested in 3 months. Plus, you should also be able to differentiate, if it is a sarson ka khet. So I don't know how to say it in English, but if it is, do you know Nipun? Sarson ka
Yeah.
khet hai. Okay.
Mustard.
Mustard. So if it's a mustard field, then it's likely to be yellow in some time, right? But if it is a sugar cane, it's going to remain green, but it's going to grow in height. So how can you sort of put those nuanced things within the model? If it is able to do this pretext task well, then it is likely that it is learning some information about that. So in fact, we observed that on a crop yield task, which is considered to be one of the difficult tasks in agriculture, it was actually beating all of the supervised methods as well. Uh, so yeah, so this is another thing that you can sort of do with agricultural imagery. Uh, so since this is work in progress, I will sort of keep it short. Do you have any questions on this one?
Questions?
Does it capture crop rotation?
Does it capture crop rotations?
Good question. Yeah. So to make sure that it captures crop rotations, which crops are rotated with what kind of crops, we sample the T1 and T2 such that they remain in a 3 month period, which is typically not the period where you do rotations. So we've tried longer periods as well as shorter periods, but this seems to be the sweet spot in terms of learning maximum out of it.
I have a rather naive question. Is this imagery taken at the same time? Like, so are the other external conditions similar so that the only change which is happening is due to the cropping, etc., not day, night, etc.?
Yeah. So the Sentinel, so the planet scope images that we were looking at, we tried to ensure that they were roughly at the same time. But there is some variation there which you can't really control. So we do expect the network to be able to do invariance of the illumination as well. Okay, so this is the bottom-up part where you actually do a case study, and you would realize that to do the bottom-up thing, you require a lot more people, right? So you will see a longer list of authors here. Uh, we had to do this water and nitrogen stress estimation for farms. So we were working with a farmer who has a huge farm and was kind enough to give us almost 16 acres of their land to do this test setup. And you will notice the different shades of blue is basically more water, and the different shades of green is the more green it is, the more nitrogen. So we set up this entire test farms with controls in terms of how much water we were giving it. And we observed drone imagery over an entire cycle of 12 months. Sugarcane is a long crop. It is an annual crop. So it takes 12 months to mature. And these are some other images from the test farm setup where, at least the PhD student Rajiv was going every month to do the drone imagery. And he had never imagined that a computer vision PhD could entail all of this. So this is the test farm layout. These are the different types of applications that we did in different farms. And we used this drone. We did a temporal resolution of 1 month, and we did 5 bands of data: blue, green, red, as well as red edge and red IR. So in the exploratory data analysis, we did find deviations in terms of the R, G, and B. They did appear to be different for the different categories of data that we had. And yeah, so the medians are also slightly different, but this is in the raw pixel space. We were just trying to see whether whatever model we are building will even have a chance of working. So the nitrogen application that you do is basically going to affect how tall your crop also grows because it is lesser nutrient. So we also took ground truth samples of the cane height uh, by taking a random sample within these different areas. And we also did LWC analysis, just leaf water content. This is to quantify whether the water that we did not put actually showed up at the leaf level or not. So to do leaf water content, you basically take out leaf samples, then you dry them in a microwave, and then you take the difference of weight before and after the drying. That's how you get the leaf water content, right? So these are more sort of micro level experiments to determine whether what we're doing is correct or not. And finally, we also looked at the yields per region. And yeah, so then the rest of the job was simple. We trained a basic CNN model to do this 9-class classification between the different 3x3 classes that we had for water and nitrogen. And we found that at a pixel level, we got about, I think, 65% accuracy. But at a cluster level, we got much better accuracy. So you can see that roughly the colors that you see here, which is the ground truth colors, are similar to the colors that we're observing at a pixel level at a slightly aggregated level. Okay, and this is what we were able to do from the satellite imagery. So this also came quite close to this particular thing, indicating that it might be possible to detect this from the satellite imagery. Although you are at a severe risk of overfitting here because your samples are much lesser than the number of possibilities that you might have in the open world. Okay, any questions on this work?
Any questions? No, I think no
All right.
questions.
Okay, so I guess people are getting tired. So let me try to speed this up a little bit. So the other work that we're trying to do is lake and water body estimation. So another thing that you can segment very well from satellite images is actually water. And there are two tools that we built out here. One is a simple, you draw a bounding box and it gives you the entire time series of this particular lake. So this is again being pitched as a tool for the municipal corporation to figure out whether the kind of efforts that they're trying to put in are correct or not. And this is a river analysis platform. So we mark different intersections of the river, and then we try to see how width as well as sort of land use has changed around it. So there is an experiment that's going on with the Center of Water Security at Laksha. So they are looking at a stream, which is a 15-kilometer stream around the region of Laksha. They're trying to figure out how this particular stream has changed over the past 15 years, and how the occupation and sort of the other dynamics around have changed because of the change in water quality and things like that. So we are creating a lake dataset. Currently, the datasets that are available in public are using NDWI, which is a geospatial index, as the ground truth, which is just a pixel-based manipulation. So it's not a great ground truth. So we are building that, manually annotating these water bodies right now. This is the distribution of the size of the water bodies. And when we realized that, okay, a lot of our lake sizes were very small, we also started looking at whether we can use this for detecting urban waterlogging. So can you actually detect waterlogging within the city using similar approach? So, so here actually the problem was that we were trying to correlate with the rainfall data. And unfortunately, whenever there is rainfall, you will also have clouds. So you did not see anything from the from the satellite imagery, and therefore we had to switch to radar. So this is the RGB image that you see, and this is the radar image that you see. So you can see the radar actually is passing very well through the clouds, and it is also able to detect whatever is underlying. So we are actually now working on doing a radar based water segmentation. This is useful for two aspects. One is, of course, when you have cloud cover, but even in forests where you have very dense canopy, you are not able to see through the canopy to detect the water body. And it's more of a problem there because if you don't have enough water in different regions, then the wildlife also starts migrating. So that also becomes a problem. So yeah, so we are building a SAR-based urban waterlogging detection for lakes as well. Any questions on water?
Any questions? No. I have a few
Okay.
comments, but I'll discuss them one to one, especially on
Okay.
SAR.
Sure. And finally, I would just like to thank the team who's been doing all of this work. A lot of them are UG students, and I have some full-time research fellows. So we call the people of the group as geo visionaries because they do geo vision. So here we are, and of course, the lake team is called hydro visionaries. It's to their own naming. I'm open to any other questions now.
Okay. Overall questions.
So how is the effectiveness of the hotness in the cities?
How is the effectiveness of?
So so we have checked that someone has put some roof or not, but how we are, I mean, then checking that the city is becoming the colder.
Okay, the question, I'll just repeat the question.
I got that, Nipun. So,
I just repeat it for the recording purposes.
okay.
So how can we check whether if such interventions are done, then the actual improvement happens in terms of the energy and the temperature reduction, etc.
Great question. So in fact, the question is also more nuanced that what is exactly the intervention? For example, planting trees or putting cool roofs. What is the intervention that will actually reduce atmospheric temperature? So unfortunately, that happens to be a tricky question to answer because the microclimate depends on a lot of things. Whether there's a water body nearby, do you have plants nearby, things like that, right? So right now, this has been published in various papers as different kinds of. So in this region, whether it works or not, and so on. But you can't really do a large-scale cool roof deployment with it before you check the change in degrees. Right, so now we're working on sort of microclimate simulations where we could do some of these interventions. And so if you've heard of GraphCast or some of these physics inspired neural networks that people have been building out for climate forecasting. We're trying to use similar things for microclimate modeling within the cities and sort of do a cause effect analysis. Although we did find from satellites you can see something called land surface temperature, and land surface temperature is the 160-meter pixel where you can get the temperature, and we did observe that it was actually cooler on top of the cool roof itself. It doesn't say anything about the air temperature nearby, and the air temperature is hard to predict from the surface temperature. But LST reduction is a indicator that you might be able to use this technique for something else.
Okay, other questions? So I have one request for you, Anupa. Given that this course is AI for social good, and our audience is mostly students who are trying to get into this area, trying to understand the nuances, trying to understand the research, also trying to understand that how much of domain expertise is needed. So do you have any advice for the students sitting here?
I'm still figuring out that myself. How much of domain expertise do I need? But yeah, I mean, the only advice that I would have is uh, you just put voluntary thought in terms of societal problems that you see around you, and see how you could use the technologies that you're looking at, that you're learning here for use within them. That's a very sort of general cliched statement, but yeah, that happens to be the case for most of the work that actually came out from the lab as well.
Okay, so let's thank Anupam for this wonderful presentation. And we've seen a huge array of sensors. We have seen a lot of, as you mentioned, geovision and hydrovision kind of works. We've also seen we've seen some field deployments. We have seen some actual literal field deployments and some deployments with respect to the cool roofs. We have heard a lot of municipal bodies today. So this is perhaps the most number of municipal bodies you might hear in any talk here. So I think this clearly shows that it is not just getting the technological problems might not be the hardest, it's the other problems, reaching out to the stakeholders. And as we also heard in the previous speakers, so we engaging with the right set of these stakeholders is going to be important. And very happy to see Anupam's work where they're actually doing that. And a little jealous of them also because they have these farms in the campus where they can do controlled trials. So let's thank Anupam.
Thanks a lot, everyone.